happy Thanksgiving. I hope everyone is enjoying the Thanksgiving time with your families and having a good time, and then resting time and preparing for strong for the end of the semester. Classes will resume on Monday. We are meeting on Tuesday, starting off with the final presentation for 15 minutes and transitioning into chapter 8. Now, sections of chapter 7, as I mentioned in class, will be explained using the video recording. Will be a couple of video links. I will try to make them shorter so you don't have to spend like hours watching. And then I'm going to go over some important topics related to chapter 7, and then in general the graphs, but graphs defined in the graph theory. We went over definitions of graphs and graph theory, the way we define graphs by using vertices and edges, notations of the graphs in the graph theory, different types of graph. We did spend time in class before the presentations. It's been a while, but I will strongly recommend everyone to go back and look at them. So let me finalize with 3 more different types that I was not able to finish during the time that I went over the graphs and then the types of graph and definition notation. And then I'll transition into section 7.2, connectivities, the paths, and the circuits. I did mention one important fact that kind of like relates to the history of the graph theory and how the graph theory was actually created for the first time, going back to the 17th century. One mathematician, Swiss mathematician Euler, um, provided a solution to one application that is well known. And then I remember going over in class and then explaining um, some history of that particular application. But Euler provided a solution of Königsberg's bridge application. The Königsberg bridge application is based on a made-up story of people wanting to stroll through a park, as I remember explaining in class, a park with 5 bridges. Now, this Königsberg theory of bridges sometimes includes 7 bridges, but what is important in what I'm explaining is an odd number of bridges. And then people trying to stroll through a park with 5 bridges in the way that all people could cross every of the 5 bridges exactly one time, and then end up after um, strolling through the park, ending up to the same location, to the same initial location. Now, this story, as I said, is well documented. I did share some Google search about the story, and then the mathematician who provided the solution of this particular theorem that later on became the Euler's theorem. The Euler's theorem showed, and then the Euler's proof showed that there is no solution of this particular application. But we'll get the opportunity as part of section 2 to go some definition of the Euler's path, some important Euler's theorem, and then definition of the Euler circuit, and then some examples to identify Euler path or a Euler circle. So we'll go over, as I'm going over, not really the proof of the theorem. I will try to define the theorem, the conclusion of it, what is given, explain it, and then use the example to explain in every single case all these theorems that I'm about to share with you. So let me go ahead and then start sharing. As I said, I will start off with let me go back to screen. Now I'm sharing. Yeah, I'm sharing the screen. So this is the graph theory. This is section 7.1. By the way, these are all scanned and posted in Brightspace or whatever I'm going to go over, with the exception of 7.5, which I'm going to go over, but as far as the additional notes, I will scan them on Monday. I'm also scanning on Monday solutions of quiz number 10, which is the final quiz scheduled for next Thursday, December 5th, which is the final day of class for us. And then 2 files are posted in Brightspace. I did post them last Wednesday. One is a file for the study guide of quiz 10. As I said, the detailed solution will be posted, scanned, and posted early morning on Monday once I get access to my office and the scanner. And the final exam is also posted. So you get the opportunity, you probably have the opportunity to find and locate them. I did send an email notifying everyone that these 2 files now are available. Now, once we finalize this semester on December 5th, which is Thursday of next week, almost 7 days from today, then I will start scanning the solutions of the final exam. I'm going to start working with the detailed solution of the final exam between now and Monday, or maybe between now and Tuesday. My goal is to scan the first part of the solution so I can get you to do some work with and some study with the final exam study guide. And then the second part of it sometime at the end of next week. Okay, so as I'm scrolling all the way down, now you see these examples, connection graphs, the simple graphs, the multi-graphs, the pseudographs. Now I'm going to transition so many examples that we went over in class, and feel free to go back and look at them. I'm going to transition to the final part of it, and this is where I stopped. So these are some other graphs, one of them common graphs, one of them is the complete graph. Now the complete graph, it's a type of graph that consists of, it is a type of graph that consists, there you go. It was blocking, but I was trying to say, consists of vertices that are connected together in the way that each vertex has 2 edges. So let's start with their notation of the complete graph is K, and then N shows the number of vertices. So let's say N is the number of vertices. Now, if N is the number of vertices, then we say the general notation of the graph becomes Kn with an index N. So this one, as I said, the graphs that are not of the type Kn, or the complete graphs, connect every possible pair of vertices. So you see there's connection outside and then inside. So if there are 3 vertices, n is 3, this is a triangle. Notice that from each vertex, there are 2 edges. So 2 edges from each vertex. So the number of edges is indeed n minus 1, which is number of vertices minus 1. If I have a graph with n equals 3 and vertices, we call this K3, and that's more like a triangle style. Now, if the number of vertices becomes 4, then the notation is K4. Now, question is, again, do we have 2 edges from, do we have n minus 8 minus 1 edges from each vertex? So the number of vertices is 4. So, what is the number of edges from each vertex? So I'm going to do n minus 1, which is 4 in this case, minus 1, 3. So I'm expecting to have 3 edges from each vertex. Is this the case? So let's focus on the upper left vertex. I count the edges. So these are line segments now that are connecting 2 edges that later on you will learn that these are known as the adjacent edges. But the top left corner is connecting with the bottom left, is connecting with the top right, and then it's connecting to the bottom right. So there are 3 edges from each vertex, and that's the case. So if you start with the upper right vertex, it is connecting with the upper left. It's connecting diagonally with the lower left. It's connecting, falling to the right with the lower right. Now, if n is 5, then the graph is a K5. The number of vertices is 5, so we are expecting how many edges from each vertex? N minus 1, which is in this case 5 minus 1. We are expecting 4 edges from each vertex. Let's look at this top edge. This is the pentagon style with the diagonals inside of the opposite vertices. So if I look at the top edge, this is connecting to the one to the left. It's connecting to the one to the right. These are the outside edges. And then inside 2 diagonals. So 1 to the bottom left and then 1 to the bottom right. So altogether 1, 2, 3, 4, which is, if for n is 5, there are 5 vertices and then n minus 1 edges, which in this case is 5 minus 1 equals 4. So in general, for n vertices, we have the number of edges equals to n minus 1. And therefore, to find the total number of edges, we multiply the number of vertices by n minus 1. So for each vertex, we have n minus 1 edges. If I'm going to have n vertices, how many total edges? It's going to be the number of vertices times the number of edges for each vertex. But notice one thing, notice the division by 2. How come? Because if you're paying attention to these particular graphs, we must divide by 2. If I look at the graph that is the easiest one to understand, the triangle, and then look at this vertex graph that is the top one, it's connecting with 1 edge because this is a graph that has 3 vertices, n minus 1, which is 3 minus 1 edges. So we are expecting 2 edges from each vertex. But this top vertex connects with the one to the left, and then the one to the left connects with the top. So these particular vertices are connected by edges, but 2 vertices, every two vertices are connected by the same edge. So we do not count them twice. So therefore we divide that by 2. So after we count the number of edges, which is for n vertices is, for one vertex is n minus 1. And for n vertices is going to be n times n minus 1. So the number of edges times the number of vertices. We have to divide this by 2 because every 2 vertices are connected by the same edge. So we don't have to count the same edge twice. Now let's transition to another type of graph known as a cycle graph. Now, if you pay attention to the complete graph and the cycle graph, if I look at the case of a pentagon, 5 vertices, then you notice that we have outside edges and then inside, the ones that are connected diagonally. That's no longer the case with the cycle graph. With the cycle graph, let n be the number of vertices again, but we only connecting every vertex to others going around without connecting inside edges. So the diagonals are not going to work. I'm aware that, and you should be aware that for K3, which is the number of vertices 3, you only have outside edges. There's no way you can connect inside. But once you get to 4, 5, and so forth, you notice that there are insides for the complete graphs, the ones that are we refer to as the diagonals. So this upper right is connected with the lower left. That's a diagonal. That's an inside edge. That's no longer the case for the cycle graph. You're only connecting with the outside edges. So in this case, we are expecting the number of vertices and the number of edges to be equally the same. So this is where the shapes, well-known shapes in geometry, are coming from. So they're coming from the cycle graphs. So the first shape, which is a triangle, there are 3 vertices, 3 edges altogether. So the number of edges and the number of vertices is 3. The cycle graphs have a notation C for the word cycle. This is not the case for the complete graph. We do not call the complete graphs with the letter C. We use a letter K, so we can distinguish them from the cycle graphs. And if the number of vertices is 4 and you're connecting with the outside edges, then you're expecting to have 4 edges. That's a typical quadrilateral. Quadrilateral means 4 edges, 4 vertices. And the pentagon is an example of 5 edges, 5 vertices, and that's a C5. So C3, C4, C5. So what is a CN? A CN has n vertices, so V is equal to n, and then n edges, E equals to n. And then I'm going to conclude with the wheel graph, another interesting graph using, as you notice, the same shapes, but what is different now? It's not that you're connecting inside diagonally, but you locate the center of each shape. So if I look at the cycle graph, for each of these shapes geometrically that I included in the cycle graph, you are going to find the center of each of these shapes. And then once you locate the center, all the vertices must be connected to the center. So you're creating the edges that connect each vertex with the center of this particular graph or this shape. So we find the center of the triangle, and in addition to connecting the vertices with outside edges, so 3 vertices, 3 outside edges, we are going to connect each vertex with the center. So we have 3 additional edges that connecting each vertex with the center. Now the wheel graphs, we denote them by W. So if the number of vertices is 3, we call this W3. Now, if n are vertices, notice that the number of edges is doubled. So you have 3 outside edges plus 3 inside that connect each vertex with the center. So if we have 3 vertices, then we have 6 edges. Let's see if this is the case for number 4. So W4, we have number of vertices is 4. Center is not part of what I refer to as a vertex. This is called a center, so be very careful. So we are connecting the outside vertices. We connecting the vertices with the outside edges, but then once we locate the center, each vertex is connected with the center. So there are 4 edges outside and then 4 edges created by the connection of each vertex to the center. And that's the case with the center of the pentagon. You connect with 5 edges outside or 5 outside edges, and then you connect each vertex with the center for an additional 5. So 4 vertices, 8 edges, 5 vertices, 10 edges. So the idea is if I have n vertices for the wheel graphs, the number of edges is going to be twice the number of vertices. So therefore, if V is n, the number of edges E is going to be 2 times n or 2n. So I hope everyone this is the final part of section 7.1, going over specific graphs. Feel free to look at my additional notes in addition to what the unit lessons are including for section 7.1. And now I'm going to transition to the first part of section 7.2, where the focus is going to be on connectivities, the paths, and the circuits. Let's start off by providing some important definition. I'm starting with example 1, where you see a graph. Edges are connecting vertices A, B, C, D. Now let's focus on this graph to answer the following question. Is vertex A adjacent to the vertex B? We are familiar with the word vertex, but what is adjacent? So A and C are called adjacent if there is an edge connecting A and C. So we respond yes, because the edge AC connects directly A and C. So these are known as adjacent if there is an edge directly connecting vertex A to vertex C. Now let's look at, for a better understanding, is vertex A adjacent to B? Is vertex A adjacent to B? Unfortunately, the answer is no. There is no direct edge connecting A to B. A and B are connected indirectly from A to D, then D to B. So therefore, A and B are not adjacent. So that kind of like allows you to understand the concept of two vertices being adjacent to one another. And then the adjacency is going to show up later on when we study the connectivities, the path, and the circuits. And of course, we'll define what the connectivities are, what the paths are, what the circuits are. Now, let's look at edges being incident to the others. So is edge BD incident with vertex D? What is exactly for the edge BD to be incident with D? So the edge BD incident to the vertex D. The answer is here is Y, because D is a vertex that connects vertex B and D. So in this case, we say the edge BD is incident to the vertex D. Is BD incident to A? So is this edge incident to A? The answer in this case is no, because there is no edge connecting A and B. So connecting A and B. So therefore, A is not a vertex connected by the edge BD. So the edges that are incident to vertices are edges that have a connection with that specific vertex. You probably argue that D does, but B doesn't. Now let's transition into the definition of a circuit. We define a circuit or a cycle to be a path that starts and ends at the same vertex. So let's see if there is a cycle or a circuit in the above graph. I want you to focus on ACDA. So A, so the idea is you're connecting all vertices, but you're connecting them in the way that you start with the same. I'm going to focus on ACDA. So I start with A, I go to C, I go to D, and then I come back at A. So ACDA is indeed a circuit in that particular graph. For each of the graphs below, determine if these graphs are connected. So first I'm going to share the images of them. So we have three graphs, G1, G2, and G3. And then as I go over one by one, I will look at the explanation in the next step, in the next page, and then try to explain it to you by simply showing you and displaying the graph that is going to allow me to explain the reason why. So the idea is, are these graphs connected? Let's focus on G1. So is G1 a connected graph? So this is all about the connectivity of the graph. The answer is no. The G1 is not a connected graph. Why? Because there is no path from C or D. So I can connect C to D and D to C, but I won't be able to connect it with the other vertices A, B, E, and F. So if I take a path from C, I won't be able to connect with A. Now let's look at G2. G2. Is G2 a connected graph? The answer is yes. G2 is indeed a connected graph. There is a path that starts with a vertex A. So I go to F, I go to D, I go to C, I go to E, and to B. So there's a path starting at A, ending at B. So G2 is indeed a connected graph. Is G3 a connected graph? Obviously, the answer is no, because there is no path between A and B. I mean, I can go from A to E and from A to D and H, but there's no way I can go from A to B. So G3 is not a connected graph. Now we're going to focus on another important, and these are all the explanations that I just went over. Now, another important concept is the concept of a cut vertex and then a cut edge. So what's the difference between them? Not a lot of differences. They use the same idea. So your goal is to look at one graph as we are going to do it, and then remove one of the vertices. And then the idea behind it, the vertex becomes a cut vertex if after removing it, you're disconnecting the graph. It is the same idea with the edges. When you remove an edge, the edge becomes a cut edge if the removal of that particular edge is going to disconnect the graph. So let's focus on the graph below. And then I will do vertices, some of them, and I'll encourage you to do the other ones on your own. It's a good learning process and then allows you to understand the connectivity of the graph and the concept of a cut vertex and the cut edge. So I'm going to start off with vertex A. I write, in general, I like to do this alphabetically. So if we have to test out, because when you're looking for cut vertices or cut edges, you have to go through the entire graph and then try to study every single one of those and then explain if they are in the category of a cut vertex or a cut edge or not. So you kind of like categorize, but you have to go through every single vertex, every single edge of the graph. So vertex A, I start off with the vertex A. Remove vertex A. If I remove the vertex A, then the rest of the graph will still be connected. I can still go from B to C to F to H to D to E. I mean to G to E to D. So I start at B. So let's say we are removing A. So this AB edge is going to be fully removed, right? So is A cut vertex? If I remove this, this edge is gone. So think of this as a bridge, right? So this part is gone. So now, or a stairway. So now I'm going to start at B. Is the graph still connected? Am I going to be able to reach to all the vertices to see that connectivity? So I start at B, go to C, go to F, go to H, go to G, go to E and D. So the graph stays connected. So therefore, A is not a cut vertex because removing A is not going to impact the connectivity of the graph. Now let's look at the vertex B. Let's say I'm removing vertex B. So when I remove vertex B, what are the edges that are impacted? B has 3 edges connected. It's connected to vertex A with 1 edge, connected to E with an edge, connected to C. So therefore, I'm removing edges AB, BE, and BC. Is the graph still connected? So the edges that are removed are AB, BC, and BE. So I start at C. Can I go to D from C? Even though this edge right there, this one right there, and this one is removed. So I go from C to F, that's okay. From F to H is okay. From H to G is okay. From G to E is still available, and E to D. So the graph stays connected. Therefore, B is not a cut vertex, even though I removed 3 edges. By removing B, 3 edges are impacted. I'm going to test vertex C. Now, vertex C is connected to B and F. So that means removing C is going to disconnect B. It's going to remove H, B, C, or CB and CF. Then you see all of a sudden this HAB fully get disconnected. So let's find out. So AB is going to stay. So I go from A to B. Then I go to E. Then I go to F. Then I go to H, to G, to E, to D. So the graph still remains connected. So I was able to, so I started at F, H, G, E, D, even though I started at B. So B, E, F, H, G, E, D, even though this, I'm sorry, I started at A. So A, B, E, F, H, G, E, D, even though CB and CF are removed. So stays connected. B C is not a cut vertex. And then finally, let's look at D. This is where D is. So I remove C. C is not a cut vertex. So now I'm going to remove D. D is removed. So therefore this HD will be removed. But that's okay. The graph is going to continue to stay connected. All vertices are connected. So there's a path from one vertex A to vertex E. Now I have to back up to the vertex B because if I remove B, then BA age is gone, BC is gone, BE is gone. Now, vertex C and E stay connected with the graph, but A is the one that cannot be connected. A is going to be alone. It's a single vertex, so B is indeed a cut vertex. So I was able to find the cut vertex. Now I did A, B, C, D. I will encourage you to do E, F, H, and G. It's a good exercise and then a good way to understand connectivity and then the cut vertex. So let me transition to another example. And then, by the way, you have vertex A removal. So it's not a cut vertex. Vertex B, as I said, the graph is no longer connected because vertex A is outside. It's just alone. So B is defined as a cut vertex. As I explained, C is not, and then D is not. And I'll encourage you to check the remaining vertices. Now let's look at an example for the graph below. We are not identifying the cut vertices. We are identifying the cut edges. So just like cut vertices, for cut edges, we must go through each edge one at a time to see if removing it causes the graph to be disconnected. That's the whole idea behind it. So we're going to start with edge AB. I'm going to continue to display the graph even though the explanations are in the next page. I'm going to continue to display the graph and then go over how to show you. So if I remove HAB, that means vertices A and B after removing HB are still connected through other edges because A is not only connected to B, it's connected to D. So if I remove this AB, so A is not going to be isolated. A will be connected to D and B alone will be connected to E. They're not connected between each other, but they're still connected to the graph. So therefore, AB is not a cut edge. Now let's look at AD. Is AD a cut edge? So if I remove AD, now the question is, am I connecting these vertices A and D again with the rest of the graph? So if edge AD is removed, A is still connected with B, and then D is still connected with E. So connectivity of the graph is still there. So therefore, AD is not a cut edge. The next one is HBE. So it's the one right there. If I'm removing this, B is still connected with A, which is connected with D, which is connected with E. Even though they're not directly connected together, B and D are staying connected with the graph. So B is not a cut edge. So I'm going to transition into EF. If I remove EF, that's critical. Because if I'm removing this edge, this piece, which is like a rectangular shape, this piece that has vertices A, B, E, D is going to be separated from the piece that has this triangle shape right there, G, H, F, and then this extended edge from F to C. So there's two separate pieces. They're not connected together. So therefore, EF is indeed a cut edge. Now, as I said, I'm going to show you. So these are all the explanations that I just went over, but at the same time, I want you to practice with CF, FG, FH, and GH. I'm just providing the answers out of the 4 edges remaining. three of them, if you remove FG, FH, and GH, the answers are going to be no. So they're not cut edges. They're not classified as cut edges, meaning if you remove them, there's still connectivity of the graph. But the CF, if you remove it, that's going to create a graph that is disconnected. So the answer will be yes, that is classified CF as a cut edge. Feel free to look at this the way I did it with the other four edges. It's a good exercise and then a good way to understand this process. As we transition into an important definition, and this definition is extremely important for all the theorems and then a variety of examples that you will see as part of section, not only section 7.2, 7.3, and 7.5. By the way, we do not go over section 7.4. The number of edges incident with the vertex V is called degree of a vertex, and then it is denoted by that's a typo in there, is denoted by DEG, not DIG, DG of V. So for each vertex, we are going to see edges that are incident with the vertices and then determine what the degrees are going to be. And then as we look at them, so this is a graph with 1, 2, 3, 4, 5, 6 vertices. Let's do this alphabetically. So A, B, C, D, E, F. And then for each one of them, we count the number of edges incident to each vertex. So what is the degree of vertex A? Obviously, there's only one edge from A to F. So A is connected by F with one edge. Therefore, the degree of vertex A is 1. That's an odd degree. So the number of them represents the degree, but you, based on that number of the degree, you should be able to say if the degree is odd and even or even. And that's important sometimes when you identify some important paths that we are going to study as part of the remaining of section 7.2. Now let's transition alphabetically to B in alphabetical order. There are two edges incident to the vertex B. That is BC and BE. So the degree of B is 2. That's an even degree. There are two edges incident to vertex C, CB, and CD. So therefore the degree, also the CE, I'm sorry, so CB, CE, and CD. So the degree of C is an odd degree equals to 3. We transition into the vertex D. There are two edges incident to the vertex D. So the degree of D is 2. Transition into E, there are two edges incident to vertex E, degree of E is 2. And transition finally to F. There are two edges incident to the vertex F, degree of F is 2. And then you have all of them one by one, and then you have the right notation, D, E, G. Now, let's determine the degree of each vertex in the graph below. Let's start with V1. V1 has a degree 4. How come? You have these line segment edges that are connecting V1 with V2 and V3, but then you have the loop connections, 2 of them from V1 to V3. So there are 2 loops plus 2 straight or line segment edges, 4 altogether. Degree of V2 is 3. There are 2 edges connecting V1 and V2, V2 and V4, and there's a loop connecting V4 and V2 and V3. Now the degree of V3 is 4. Why? Because there is a straight edge line segment connecting V3 and V1, but V3 and V1 are connected by 2 loops, left and right. So there's 3 right there between the connection of V3 and V1, and there's an additional loop connecting V3 and V2, so there's 4 altogether. And now what is interesting is V4. Anytime you have a pseudograph such as this one, what is a pseudograph? When you find loops that are connecting the graph to itself, that counts as 2. because you started V4, you're coming back at V4. So that's a full loop 2. And then there's one connection to V4. So therefore, we have a degree 3 for the V4. And based on the degrees, we have this important theorem known as the handshaking theorem. For a graph G with n vertices and e edges, the sum of all the degrees for all vertices from 1 to n. So I is the index representing the number of vertices. So we have V1, V2, V3, V4, Vn. So that means n vertices. So the summation of all the degrees is equal 2 times the number of edges. So that means the sum of the degrees is always an even number. And then it is equal to twice the number of edges. Let's determine how many edges are in this graph below. Now you can do this by observation. You can start counting the number of edges directly, but sometimes gets very tricky, such as in graphs such as this one, and then even more complicated. Why? Because you might end up counting the same edge twice. There's a high chance of doing that, or there's a very high chance of missing one of those edges. So to avoid that scenario, it's better to use what is known as the handshake theorem. So what you need is, in order to get the sum of the degrees, all you need to know is how many vertices are in there and the number of edges. And then all you have to do is multiply the number of edges by 2 to get all the degrees. Now, if you can determine the degrees, which is more obvious because of the graphical presentation, then you can find the edges, add up all the degrees together, and divide the sum of the degrees by 2, because the sum of the degrees is 2 times e. So to find e, the number of edges, you divide the sum of the degrees by 2. The number of edges is half of the summation of the degrees, and that's what I'm going to do. So if I look at this particular graph, there are 1, 2, 3, 4, 5, 6 vertices. Now for each vertex, notice a number inside parentheses. That number represents the degree of each vertex. The vertices are not named, but you see the number inside parentheses representing the degrees of each vertex. So this particular vertex has 3 edges, therefore degree is 3. Now this one is 5, 1, 2, 3, 4, 5. Now this one has 4, 1, 2. These are the outside and 2 inside. This vertex has only 3, all 3 insides. This vertex has only 2, both of them inside. And then this one has 2 outside, 1 inside, 3. So what is the total number of the degrees? I'm going to add up these numbers. So 3 plus 3 plus 3 plus 2 plus 4 plus 5. Altogether is 20. So the sum of the degrees is equal to 20. Now we know that this sum is 2 times the number of edges. So that means I'm going to set the summation of all degrees. By the way, this little I, which is on the index, shows how many vertices. There are 6 vertices. So we have a vertex V1, V2, V3, V4, V5, V6. That's why you see the index I representing each vertex notation is from 1 to 6. There are 6 vertices. Their degrees are added up, it's 20. And then we know from the handshake theorem, the sum of the degrees of all vertices is twice the number of edges. So that means the sum is 20 is going to be 2 times the number of edges. So what is the number of edges? It's 20 divided by 2. There are 10 edges altogether. So if you do the observation method by counting them, you must find 10. But again, what is tricky in some graphs that gets very complicated, possibilities or probabilities or chances of missing one or counting one twice are very high. So to avoid that, it is recommended to find the degrees of each vertex, which can be easily done. If you go through the image from one vertex to the other, get the degrees, add them up. So you get the sum of the degrees and divide it by 2. That's going to be the number of edges. In this case, this is an image with 10 edges. Now let's transition to the Euler's path and circuit. As I explained in class, Euler was the one as a Swiss mathematician the very first one who proved the Königsberg bridge application or problem, and then showed that this is a no solution problem. But the work that Euler did later on in graph theory are connected to identifying paths and circuits, and then bringing that connectivity of the graph into a different level in the graph theory. And that's the main reason why we always refer to Euler and the work that he did for the graph theory as the father of this large area of mathematics. Euler never predicted that the work that he did back in 17th century was going to have such a huge impact nowadays. And then I said, if there is one area in mathematics, in addition to many others, that is so popular nowadays and so connected to cybersecurity, uh, cryptography, to computer programming, computer networking, that's the graph theory. Sometimes graph theory is referred as the foundation of the entire computer science. So at that time, Euler never predicted that he was going to be considered the father of the computer science, but at the same time, never predicted that the work that he did almost 300 years ago, 400 years ago, was so important and still extremely important nowadays. It is work that stands as a foundation of what is everyone is doing nowadays as part of the graph theory and the computer science. So there are certain theorems to recognize the work of this famous mathematician. We refer to them as the Euler's theorem. And then one of them is a theorem that is for the connected graphs. What Euler was able to prove, a connected graph G has always an Euler circuit if and only if every vertex has an even degree. So this theorem, which is more like a biconditional theorem, why? The presence of if and only if tells you that if you have a connected graph, that means every vertex is going to have an even degree. Or if each vertex has an even degree, then the connected graph is going to have a Euler circuit. So therefore, the theorem works on both directions, but at the same time, what Euler did provided with this theorem, biconditional theorem, some important tools that instead of going by observation through the image to identify the Euler circuit, you have to work with the degrees of each vertex, which is a much easier way of identifying the possibility of the existence of a Euler circuit. So let's finalize by looking at an example. We're going to refer to the same image that we refer to, determining if there is a Euler circuit in this particular image. And then if so, we are going to find one. Now, before I do that, let me redefine one more time what a simple circuit is and what a simple path is. And then you can see the distinction between them. A simple path is a path that has no repeated edges. So you start with one vertex and then you end to the last one without repeating any of the edges. So in this particular image, an example of it is starting from B going to D. So notice BD is one edge. I'm not coming back to go over this BD. And then from D moving to C. And then from C going to, from B to D, and then from D to A, and then going to C. So this is a simple path because as I'm going through these vertices, I'm not repeating any of the edges. So I start with HBD, from B to D, then I transition to D to A, HDA, then I transition to A to C, and then C to D, so I'm not repeating any of those edges. So this is a simple path present in this graph without repeating the edges. Now let's see what a simple circuit is. A simple circuit starts and ends at the same vertex. without repeating any of the edges. Now let's look at this particular graph. What I'm going to do is I'm going to test it out by using the previous Euler's theorem, the biconditional theorem, where in a connected graph A, there is a Euler circuit if and only if vertices, all vertices or each vertex has an even degree. So it's easy for me to identify the degrees of these vertices. And that's what you see in the image. This vertex A connects with 2 edges, degree 2. Vertex B connects with 4. So B to A, B to E, B to F, and then B to C. So that's 4. Vertex C connects with 2, C to B, and C to F. This vertex F connects with 4. So degree of C is 2, degree of F is 4. Where are the 4 edges? F to B, F to C, F to E, F to H. Now vertex E also connects with 4 edges from E to D, from E to F, from E to B, from E to G. So that's degree 4. Vertex D connects with 2 edges, D to A and D to E. So that's degree 2. Vertex G connects with 2 edges, G to E and G to H. And finally, which means degree 2. And finally, vertex H connects with G and F. So that means degree of H is 2. So all the degrees are even. Therefore, this is a connected graph and should be a Euler circuit, according to the Euler's theorem. All I have to do is find it. So I started off with vertex B. That's why you see B circle. Now I need to start at B in order to see I know that there is a Euler circuit that is existing. So if I start at B, let's see if I'm going to come back at B without repeating the edges. So from B, I go to E. Then from E, I go to D. And from D, I go to A. Repeated edges, okay? And from A, I go to B. And then from B, I go to C. Then I go to F. Then I go to H. Then I go to G. Then I go to E. Then I go to F. Then I go to B back, which shows that edges are not repeated. You may argue and say you're repeating the vertices. Yes, I'm allowed to repeat the vertices, but I'm not allowed to repeat the edges. So I started at B. Let's do it one more time. So B, I went to E, just B, H, B, one time. And then ED, one time. Then DA, one time. AB, one time. So do not repeat the edges. You can repeat the vertices. BC, one time. Repeating means if I go from C to B, I'm not. So BC, then C to F, then F to H, then H to G. These are all one time. G to E, then E to F. I never did E to F. I did F to H, and then F to B. So you can repeat the vertices. You cannot repeat the edges. And there was a guarantee 100% from the theorem, Euler's theorem, that the Euler circle was present in this graph. All I had to do is find it, which I did it. So I started with vertex B without repeating the edges, reminding everyone vertices can be repeated. I was able to come back to B. And that's all for this lecture. I will continue with the additional lecture in a video, in another video, but that's all for tonight. And then I'll try to post the other one tomorrow. Thank you for watching.